बिस्मिल्लाहिर्रहमानिर्रहीम रब्बिश इश्रह ली सदरी व यस्सिर ली अमरी वाहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली. Assalamu alaikum. Happy Independence Day. Long live Pakistan. Today we will cover section 2.5 Acceleration from the book Physics for Scientists and Engineers with Modern Physics by Serway and Jewett, 10th edition. In example 2.3, we worked with a common situation in which the velocity of the particle changes while the particle is moving. When the velocity of a particle changes with time, the particle is said to be accelerating. For example, the magnitude of a car's velocity increase when you step on the gas and decrease when you apply the brakes. Both of these actions result in an acceleration of the car. Let us see how to quantify acceleration. Suppose an object that can be modeled as a particle moving along the x-axis has initial velocity vxi at the time ti at position A and final velocity vxf at time tf at position B as in figure 2.6a. The red-brown curve in figure 2.6b show how the velocity varies with time. The average acceleration AX average of a particle is defined as a change in velocity delta Vx divided by the time interval delta t during which that change occurs. AX average is equal to delta Vx over delta t, which is equal to Vxf minus Vxi divided by Tf minus Ti. Vxf is the final velocity, Vxi is the initial velocity, Tf is the final time and Ti is the initial time. As per velocity, when the motion being analyzed is one-dimensional, we can use positive and negative sign to indicate the direction of acceleration. Because the dimension of velocity are L over t and the dimension of time is t, acceleration has dimension of length divided by time square or L over t square. The SI unit of acceleration is meter per second square, m over s square. It might be easier to interpret these units if you think of them as meter per second per second. For example, suppose an object has an acceleration of plus 2 meter per second square. You can interpret this value by forming a mental image of an object having a velocity that is along a straight line and is increasing by 2 meter per second during every time interval of 1 second. If the object starts from rest, you should be able to picture it moving at a velocity of 2 meter per second after 1 second, at plus 4 meter per second after 2 seconds, and so on. Figure 2.6a, a car model as a particle moving along the x-axis from A to B with velocity vxi at t is equal to ti and the velocity vx at t is equal to tf. The car moves with different velocity at points A and B. At Ti, the velocity is Vxi and at Tf, the velocity is Vxf. Part B. The velocity time graph red-brown for a particle moving in a straight line. The red-brown line, it shows velocity time graph. The slope of the green line is the instantaneous acceleration of the car at point B. The slope of the blue line connecting A and B is the average acceleration of the car during the time interval delta t is equal to Tf minus Ti. When your friend sped up from the traffic light in the opening storyline, you found the time interval between the poles on the side of the road decreased. Is this result consistent with your expectation? Yes, it is. Each new displacement between the pole is undertaken at higher speed, so the time interval between the poles becomes smaller. In some situations, the value of average acceleration may be different over different time intervals. It is therefore useful to define instantaneous acceleration as the limit of average acceleration as delta t approaches 0. This concept is analogous to the definition of instantaneous velocity discussed in section 2.2. If you imagine that point A is brought closer and closer to point B in figure 2.6a and we take the limit of delta Vx over delta t as delta t approaches 0, we obtain the instantaneous acceleration at point B. Ax is equal to limit delta t approaches 0, delta Vx over delta t is equal to dVx over dt. That is, the instantaneous acceleration equals the derivative of velocity with respect to time, which by definition is the slope of the velocity time graph. The slope of the green line in figure 2.6b equals the instantaneous acceleration at point B. Notice that figure 2.6b is a velocity time graph, not a position time graph like figure 2.1b, 2.3, 2.4 and 2.5. As we just studied figure 2.6b, the green line represents instantaneous acceleration at point B. It is the slope of the velocity time graph at point B. Therefore, we see that just as the velocity of a moving particle is the slope at a point on the particle's xt graph, the acceleration of a particle is the slope at a point on the particle's vxt graph. One can interpret the derivative of velocity with respect to time as the time rate of change of velocity. If ax is positive, the acceleration is in positive x direction. If ax is negative, the acceleration is in negative x direction. Figure 2.7 illustrates how an acceleration time graph is related to the velocity time graph. The acceleration at any time is the slope of the velocity time graph at that time. Figure 2.7, Part A, the velocity time graph for a particle moving along the x-axis. Part B, the instantaneous acceleration can be obtained from the velocity time graph. The acceleration at any time equals the slope of the line tangent to the curve of the Vx versus t at that time. Figure 2.7a is the velocity time graph. Figure 2.7b is the acceleration time graph. We obtain acceleration time graph from the slope of the velocity time graph. At the point Ta, the slope is maximum and is positive, therefore we obtain maximum positive acceleration. At the point Tb, the velocity is maximum, however the slope is 0, therefore acceleration is equal to 0. At the point Tc, the slope is negative and is maximum, therefore we obtain maximum negative acceleration at the point Tc. Positive values of acceleration correspond to those points in figure 2.7a where the velocity is increasing in the positive x direction. The acceleration reaches a maximum at time Ta when the slope of the velocity time graph is maximum. The acceleration then goes to 0 at time Tb when the velocity is maximum, that is when the slope of Vxt graph is 0. The acceleration is negative when the velocity is decreasing in the positive x direction and it reaches most negative value at time Tc. May Allah bless us all. Thank you for watching. Allah Hafiz.